Okay, this time we're going to try a logarithmic differentiation problem. So here you see this really disgusting looking quotient, and we've got to find the derivative of it. Now, when we see something so complicated looking, we're going to want to think logarithmic differentiation. We could do this using a combination of the product and quotient rule, because there's nothing really no crazy functions going on here. We could solve it that way. It's just going to get pretty messy and pretty long. So instead we're going to try natural log differentiation. So we're going to take the natural log of both sides, natural log of y and natural log of this whole guy. And of course we're taking it of both sides because whatever we do to one side, we have to do to the other side. Now, we took this natural log because now we can apply our properties of logs to simplify things a little. We have going on here a quotient, so I can divide that apart, and I have natural log x to the fifth minus natural log of 1 minus 10x times x squared plus 2, and I should put another parentheses because all of that's in the natural log. Using more properties to break this down a little bit, 5 natural log x, power property, that can come out front. And then here we have another bit of a log property where we can split that up. So it's minus, remember it's minus this whole log, so it's going to be inside the brackets. Natural log of 1 minus 10x plus natural log of square root of x squared plus 2, close bracket. So remember, this here is minusing both of them. So I'm going to distribute that negative 5 natural log of x minus natural log of 1 minus 10 to the x, and that's going to be minus, and hey, while I'm here, I'm going to do another property. So this is the same as x squared plus 2 all to the 1/2 power. So I can bring that 1/2 out front, and I have this. And notice I got my negative distributed. And I'll put my natural log y. We have not taken the derivative yet. All we've done is take the natural log of both sides and then kind of expand. But now we will take the derivative. And we have to do it to both sides. So d dx there, d dx here. So we're taking the derivative of all of this. And remember the derivative distributes. So we're taking the derivative of all three of these guys. And this guy, of course. On this side, it's implicit differentiation. It comes out to y prime over y. All right, here we go. So this becomes 5 times 1 over x. Pulled out the constant. Derivative of natural log is 1 over x. Minus, here we have the chain rule. So that would be 1 over u, where u is our inside function, so 1 minus 10x, times the derivative of that inside function, so times negative 10. Then it's going to be minus 1/2 times the derivative of this guy, and again the chain rule, so 1 over x squared plus 2, our inside function, times the derivative of it, times 2x. So let's clean that up a little bit. 5 over x minus, well actually it's going to be plus 10 over 1 minus 10x. We have these two negatives, so they become a positive. Minus 10x. And minus, okay, so these 2's are going to cancel. X over x squared plus 2. And over here we have y prime over y. But remember, our derivative, it's that y prime. The y prime standing for dy dx. So we need to solve for that. So we're going to multiply both sides by y, and we have y prime equals y times. We copy it back down. But now the question becomes, well, what is y? We want everything in terms of x, so no y's in there. Well, y is just our original function. This guy right there. So we can just copy that down. That is x to the 5th over 1 minus 10x times the square root of x squared plus 2 times that derivative we found one step above. And that right there is the derivative of our function up here. So it took a while, but it's really not that difficult. Some sort of easy steps after we take the natural log and apply its properties. Now, of course, what we have going on here, we could make it look nicer. We could combine those fractions there, multiply in a little bit. So there are ways to make it look cleaner, but what we have there is the derivative.